Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor, Department of Mechanical Engineering of JIS College of Engineering, Collari. Today's session, we will discuss about that phase diagram. So, we are in Module 3, that is phase diagram, and today's topic is that is alloy, substitutional and interstitial solid solutions. Learning outcome: to understand the basics of alloy, substitutional, interstitials, solid solution, and Gibbs phase rule. So the content of this module is, first of all, introduction to this phase diagram, solubility limits. Next is different phases exist, phase equilibrium, and next is interpretation of phase diagrams, binary isomorphous systems, development of microstructures, binary eutectic systems, development of eutectic alloy microstructures. Next is iron carbide equilibrium diagram, and last of all, time temperature transformation diagram. So first of all, we need to understand what is the equilibrium diagram or phase diagram. Equilibrium diagram or phase diagram are the diagrams which indicates the phases existing in the system at any temperature and compositions. The coordinate system of this binary phase diagram uses temperature as the ordinate, that is y-axis, and the weight percentage of second element, that is the solute, as an abscissa, that is x-axis. These diagrams are used to find out the amount of phases exist in a given alloy with their composition at the temperature. From the amount of phases at room temperature, in a certain cases, it is possible to estimate the approximate properties of the alloy. So, and these diagrams are also helps in understanding the phenomena that occur during the rapid heating or cooling of the alloy. So this equilibrium diagram and the phase diagram, that is one of the most important objectives of this engineering metallurgy, that is to determine the properties of materials. Now this equilibrium or phase diagram are the diagram which indicates the phases in the existing system at any temperature and concentrations, and the properties of material is a function of microstructure which depend on overall composition and variable such as pressure and temperature. Hence, to determine the phases present in the material system, an equilibrium or phase diagram is plotted. Equilibrium diagram or phase diagram, it is a graphical representation of various phases present in the material system at various temperature and composition point. All these phase diagrams have temperature as the ordinate, as the, that is y-axis, that is the ordinate, and percentage composition of weight of the second element, that is solute, taken as an abscissa, that is in x-axis or x-axis directions. Now next is that is use of this equilibrium or phase diagram. The equilibrium diagram is used to obtain the following information. First of all, it shows the various phases present at different composition and temperature. It indicates solid solubility of one element in others. Third of all, it shows the temperature range over which solidification or liquidification of material system occurs. And next, that is number 4, it indicates the temperature at which different phases start to melt. Now, before we broadly discuss about that phase diagrams, so some of the basic terms are need to be defined. So first of all, that is called system. The system, it is a part of universe under the study, and it may be defined some other ways also. That is the substance that isolated and unaffected by their surroundings are known as system. It may be composition of solid, liquid and gases, or the combination so a system is capable of changing its composition, temperature, pressure, density, etc. Now the second term, that is termed as phase. So phase is a physically and chemically composition of a substance or system separated from the other portion by a surface and an interface. Each portion have different composition and properties. In a equilibrium diagram, liquid is one phase and solid solution is another phase. Next is number 3, that is variables. A particular phase exists under various conditions of pressure and temperature and compositions. These parameters are known as variables of the phase. Next, number 4, that is components. These are the substances, elements or chemical compound whose presence is necessary and sufficient to make a system. A pure metal is one component system, whereas an alloy metal is a two component or binary system. Next, number 5, that is alloy. It is a mixture of two or more elements having metallic properties. In this mixture, metal is in the large proportion and other can be metal and maybe non-metals. Next, that is which is known as solid solution and its component. So first of all, we need to know what is called solid solution. So solid solution, it is termed as that it is an alloy in which the atoms of solute are distributed in the solvent and has the same structure as that of solvent. Solid solution have different compositions with similar structure and are like liquid solution such as sugar in water. So solid solution broadly classified into the two types, that is substitutional type and interstitial type. Further, the substitutional solid solution can be separated as regular or ordered or random or disordered. Now, first of all, we will discuss about that substitutional solid solution. So, in substitutional solid solution, atoms of alloying element occupies the atomic size of base metal. So, these are further classified as, that is, regular or ordered substitutional solid solution. In this type, the substitution of atoms of alloying element is in definite order in the base metal matrix. For example, that is nickel aluminum solid solution below 400 degrees centigrade is shown as regular or ordered type. Other example, that is gold copper solid solution up to 400 degrees centigrade also is an example of regular or ordered substitutional solid solution. So these are shown as in this figure. So in this substitutional solid solution in regular, such as, for example, the substitute, that is B atoms, or in A atom as shown, that is B atom here is, that is aluminum, which is solute, and nickel, that is in solvent in order. So there is a definite order or regularity as shown in this figure. Next is, that is called random or disordered substitutional solid solution. In this type, substitution of alloying elements is in any random order in the base metal matrix. Example, that is alpha brass. So in this case, that is random or disordered case, as shown in the figure, that is zinc is a solute and copper is a solvent. The zinc are placed into the copper solvent, but they are not regular, or they are haphazardly or randomly or disorderly as shown in this figure they are situated. Another example for this randomness, that is we can give, that is nickel aluminum alloy, that is above 400 degrees centigrade is shown, that is random or disordered substitutional solid solution. Another example, that is gold copper solid solution, also above 400 degrees centigrade, shows random or disordered solid solution. So the next is, that is another type of solid solution, that is apart from substitutional solid solution, that is the interstitial solid solution. So in interstitial solid solutions, the atoms of alloying elements occupy the interstitial site, that is the vacant site of the base metal. So in this type of solution is formed when the atomic size of alloying element is much smaller compared to that of the base metal. For example, iron and carbon. So here iron is a solvent and the carbon is the solute. As shown in this figure, the carbons are so small, the in between two iron molecules they can be adjusted, and these are the examples of the formation of the interstitial solid solution occurs. So with this, that is some other parts are there, that is some intermetallic phases are also exist. When an alloying element is added to a given metal in such a amount that the limit of solid solubility exists or exceeded, the second phase appears with the solid solution. The second phase may be another solid solution or an inter. The next is, that is Hume rotary rules for solid solubility. So in the formation of solid solutions, the solubility limit of a solute in a solvent is governed by the certain factors. These factors known as Hume rotary rules of solid solubility. So they are as follows. That is, first of all, that is atomic size factor. Now, alloying elements having similar atomic size as that of the base metal matrix have better solid solubility. For a favorable solid solution formation, the difference of atomic size of solute and solvent should be less than 15%. Next is, that is chemical affinity. Elements having lower chemical affinity have greater solid solubility. Elements having higher chemical affinity have the tendency of formation of compound, and hence it restricts formation of solid solution. In general, the alloy elements located closer in periodic table have higher solid solubility. Next, number third, that is relevant vacancy. Metals having lower vacancy have more solubility for metals having higher valence. Hence, for better solubility, the base metal selected should be one that it has lower valency as compared to the other alloying element. Number 4, that is the crystal structure. As mentioned earlier, solid solution is a alloy of element having similar crystal structure. Difference in crystal structure limits the addition of solubility of element. Next is, that is phase equilibrium, that is solubility limit. So in this figure, it is shown, that is temperature and composition curve. That is, in case of water, is an solute, and solvent is in sugar. That is, solute is, that is solid, liquid or gaseous, that is, and the mixture is more than one phases, and there is a solubility limit between the water and sugar. This is as shown in this figure. The solubility limit, that is the maximum concentration for which only a single phase solution exists. Now the question arises here, that is, what is the solubility limit of sugar in water at 20 degrees centigrade? So from this figure, it is clearly shown that at 20 degrees centigrade, the solubility limit is 65% weight of sugar. So at 20 degrees centigrade, if that is composition of sugar is less than 65% weight of sugar, so that will be the syrup, that is the solution of water and sugar. And in 20 degrees centigrade, if the concentration of sugar is more than 65% weight of the sugar, so that will be the syrup plus sugar, that is in sugar that is unsoluble or not soluble fully at that percentage. So if it is more than 65% weight of the sugar. Now next is, that is Gibbs phase rule. Gibbs phase rule establishes the relationship between the number of variables, the number of elements, and the number of phases exist. And it is the mathematical expression, and it is given by, that is P plus F is equal to C plus 2, where P is the number of phases in the system, F is the number of variables that can be changed independently without affecting the number of phases, C is the number of elements, and 2, it represents 2 variables among temperature, pressure, and compositions. So out of 3, 2 variables among are there. So at constant pressure conditions, the equation will become, that is P plus F is equal to C plus 1. So in general, all equilibrium diagrams studied at constant pressure. So pressure remains constant. So out of 3 variables, that is remain 2. So hence the Gibbs phase rule modified into, that is P plus F is equal to C plus 1. So that is phase rule. This phase rule helps to determine the maximum number of phases present in an alloy system under equilibrium conditions at any point in phase diagram. The phase rule can also be used to determine the degree of freedom that can be changed. Next is Gibbs free energy for thermodynamics stability of phases. Gibbs free energy for thermodynamic stability of phases describes the amount of energy that released or consumed when a phase is created from other phases. Gibbs free energy for formation is relative value, allows us to compare energies of different phases. So by the convention of the value, that is Gibbs free energy, which is denoted as delta GF, of pure metal or element is assumed to be 0. The phase having lowest value of Gibbs phase energy is a stable phase. Gibbs free energy for thermodynamic stability of phases. Gibbs free energy for any phases varies with pressure and temperature. The fundamental relation between these is given by G is equal to E plus PV minus TS. That is, we can write that is del G, that is in differential form, equal to del E plus P of del V minus P of del S, where G is the Gibbs phase energy in joule per mole, E is equal to internal energy in joule per mole, P is equal to pressure in Pascal, V is the volume in centimeter cube per mole, T is the temperature in degree, and entropy is joule per degree mole. Gibbs free energy for thermodynamic stability of phases. At high temperature, phase with the entropy, with high entropy are very stable because TS diagram in equation has negative sign. Similarly, at high pressure also, phase with high volume are unstable because PV term has positive sign. The Gibbs free energy tells us whether a reaction will takes place or not. So with this, we are likely to conclude this session. Thank you for joining this session.